Hello everybody, my name is Love Deva and I am a student in VIT Chennai. So what we are going to see today is algorithm which is called Elgamal digital signature scheme. So it is a part of a digital signature algorithm. There are total of three algorithms. So it is a part of that three algorithms which are used to sign digital cryptocurrencies and assets. So let's have a look at them. So moving to the introduction part, so as we can see, digital signature is a mathematical scheme for demonstrating the authenticity of a digital message or document. It consists of three algorithms, which we said as earlier. We will see the types of algorithms later in the video. So it consists of three algorithms: hashing algorithm, signature generation algorithm, signature verifying algorithm. So hashing algorithm, signature generation algorithm, and signature verifying algorithm. Okay. So digital signature scheme. So there are total three digital signature schemes, which are called Elgamal digital signature scheme, which will be the main focus of the video of ours, and the other two are Snor digital signature scheme and digital signature standard DSS. So these are the three total schemes. All these three schemes are very useful. Elgamal is a bit outdated as of now, but it is still being used, and the other two, the main focus of the industry as of now is the digital signature standard. So but that is outside the scope of the video, so we will focus on the Elgamal digital signature scheme in this video. So let's see the basic structure of the Elgamal digital signature scheme. So what it does is, in this scheme there are three keys. So E1, E2, P is a public key and D is a private key. So let's see the working with a diagram sort of thing. So S1 and S2 are the two signatures. It has basically two parts. One part is called the signing part and the other part is called the verifying part. So let's see. So S1 and S2 are the two signatures, and M is the message. E1, E2, P, as we saw, are the public keys. So D is the private key and R is the random secret, which is the random number between a function. So function is called generally fine, and the random key should be between those limits. So as we can and also another property of a random secret is that it should be of a bit, at least 2048 bits. So one constraint is that, and the other constraint is that using that secret key, it should be easy to calculate the hash function knowing the private and the public keys, but it should be infeasible to find or crack it. So we have to search a number which should be of minimum low entropy. So then it would be feasible, minimum high entropy, which would then will be feasible for the selection. So let's see. So E1 is a public key, as E1 and P are the public key as we saw in the above, and R is the random secret. So using these three parameters, we generate a hash function modded by P, which is again a public key. So we all in all we require three public keys: E1, E2, and P. So in the first signature, what we do is we take three public keys: E1, P, sorry, two public keys and a random secret: E1, P, and a random secret R. So we generate a hash function using the mod and we sign the document. So the other signature is consists of a message. We have to now encrypt the message. So how we will encrypt the message? We will use a message, we will use a private key, which is D, and we will use a random secret R. We will use one public key, which is P, which is also used in the above signature, and then S1 is the first signature. So what we will do is we will first generate a signature by using the public keys of the sender, and then we will using the public key, using the function generated by the public key of the sender, we will then construct a signature and encrypt the message using the message, the private key of the sender, the receiver secret, which is the random key between the function 1 to 5n, and then we will use a public key P, and then we will use the above signature, which was done using P and E1. So this is how we will sign the document, and once this document is signed, it is ready for the transfer, and it will be very hard to crack it unless and until someone knows the secret key, which is one drawback, or someone somehow tries to break the hash function by using a number of random keys, but the probability is very low, because you cannot just generate a number of 512 or 2048 bits to crack a hash function. It is very difficult, and it takes around 10 to the power 27 years for the same to happen using the current standards of the computers. So this is the probability that is used to break the signature, but it is very unfeasible that it will happen. So knowing that, we can move forward to the signing part. In the signing part, what we do is we use again the S1 and S2 encrypted messages which was used in signing, the E2 private key, the last private key which we didn't use in the signing, we will use for verifying. So this key will be in the database table, and we can fetch it and we can use it, but that key is to the sender, and it was also in the database, but it is to the sender, and sender use it to sign, and this we used it for verifying. So then we will use the public key P, which was used everywhere. It is a universal kind of key, so it will be used to mod the function. So the number which has to be modded will be available to everybody, but it is the keys which are hidden. So we will generate a function f3, and we will generate a function f1, and so it will use the first private key which was used to encrypt the message and the P key. So we will use f1, we will generate the f1 function and f3 function, and we will check if they are equal. If the both the functions are equal, we have successfully generated the message, but if the function is not equal, so we have not generated the message. So that is the basic overall structure of the Elgamal digital scheme. So this is how this scheme works, and once we are clear with the concepts, we can move forward. So the verifying and signing part, as we saw earlier also, we use two signatures to first encrypt a message. We will first use the keys to generate a signature, and then we will use that signature to sign a message, and then that message is ready to be decrypted. So this is what we saw. So let's see here, verify and signing. So M is the message, S1 S2 are the signatures, and V1 and V2 are the verifications which we receive from the verifying function. So R is the random key, D is LE's private key, and E1 E2 P and the public keys. So what we did in signing was the signer has to use the first public key and into the power random secret mod P. So this generates the signature 1, and then M minus DS1 into R to the power -1, where R is the random private key, mod P -1, P is the other private key, a public key. So we will use that to generate the two signatures, and we will pass the message. So once the message is sent, it is ready for verifying. So in the verifying, what we use is we use the second public key which we didn't use to sign the function, we will use to verify the function. So with that, along with the S1 which is the first signature into S2 which is the second signature mod P. So this will generate the first verification, and then we will generate the other verification by E1 to the power M. M is the message, and mod P, P is the public key. So we use these two things to basically generate the other function, and then we will check if V1 is equal to V2, then it accepts the message, and else it rejects the message as it couldn't find and verify it. So Elgamal digital. So let's walk to the theory also. So in the signing process, two functions create two signatures. In the verifying process, the output of the two functions are compared for verification. One function is used for signing and verifying, but the function uses different inputs. As we saw with E1 and E2 keys, we use two different types of keys to generate a function. The message is a part of the input to the function 2 when signing. It is part of the input to function 1 when verifying. So the calculations in the functions 1 and 3 are done through modulo P. P is the universal public key which is used everywhere. It is done by modulo P -1 in the function 2 as we saw here. So we used the modulo P -1 in the function 2, but P in the function 1. So this is what we saw. So let's see now the problems with the Elgamal digital signature scheme. So as I told you in the starting phase of the video, that the Elgamal digital scheme is not used very much because of the obvious disadvantages of the Elgamal digital scheme. So these disadvantages we will see in this chapter. So the problem is that the P needs to be very large to guarantee that the discrete log problem is interactable in ZP. So what I told you is that in the beginning is that the P has to be of a minimum high entropy. So it shouldn't be be easily to track or easily to create a random function just to solve the hash function. So it should be very difficult. So in order to be that difficult, it has to be a very large number, as I told you, of 2048 bits as of now. So to make it infeasible for the attacker to crack it, so it requires a lot of computational capacity of the functions of the computers to break it. So the recommendation of P is at least 1024 bit. Is that the minimum 1024 bit? It should be of minimum 1024 bits to be difficult to crack. But to make it, uh, to make it, which is recommended value is 2048 bits, as we are saying through the video. So to reduce the size of the signature, Snow proposed a new scheme based on Elgamal, but with a reduced signature size. So let's see the other schemes as well in just to know more about the digital signature schemes, as we have now focused on the Elgamal digital signature scheme successfully. So forgery in Elgamal digital signature scheme. So what is the forgery? So key only forgery. So in this, Eve has access to the public key. Two kinds of forgery are possible. Eve, we took the example, right? So this is all Alice private key. So Alice private key is Alice is basically a real world example kind of thing. You can imagine Alice as a person who has a public key and who generated this signature. So now we will see how forgery can happen. So there is key only forgery. So it has basically two kinds of forgeries are possible in this. Eve is again a random person. You can just imagine it. So if Eve has a predefined message M. She needs to forge Ellie's signature on it. Eve must find two valid signatures, S1 and S2, for the message. This is called selective forgery. So what Eve basically tried to do is she tried to find another signature, so which is same as this signature. So let's say Eve has a predefined message M. She needs to forge Ellie's signature on it. So what Eve has to do is to find two valid signatures, S1 and S2, which were used in the signing process to forge to forge the message. So this is called basically selective forgery. Eve must be able to find three random values M, S1 and S2 in the message, the two signatures, such that last two are the signature of the first one, such that S1 and S2 are the signature of the M. So basically it repeated the same thing, which is the selective forgery. If Eve has intercepted a message M and its two signature S1 and S2, she can find another message M dash with the same pair of signatures S1 and S2. However, note that this is also an existential forgery that does not help Eve very much. So now this is type of the existential forgery. She has to find another message M dash which has the same pair of signatures S1 and S2. So now she does not have to find the signatures, but she has to find the message which can match those signatures. So again, it is very infeasible to find another message with the two same signatures. It will be like causing your brain to work for a very minimal thing. So it will not happen, it will not work, and it is not useful. So now let's see the two other digital signature schemes in a gist. So one is the SNOR digital signature scheme, which is used for signing and verifying. The structure of this is almost same to Elgamal digital scheme with a few differences. Like here we add a hash function to encrypt the message further. So we can see in the signature we use another hash function. So it basically uses hash algorithm to encrypt the Elgamal digital scheme and to protect it more. So this is that. In the signing process, two functions create two signatures. In the verifying process, the output of one function is compared to the first signature for verification. The important point is that the scheme uses two moduli P and Q. So the function 1 and 3 use P and the function 2 uses Q. So here the function 1 and 3 uses P, and the other function, the function 2, which is the second signature, uses Q. So these are the main differences between that. So it is further elaborated as Alice uses a random number R. Alice calculates S1 H E1 to the power R mod P, and Alice calculates S2 R plus D into S1 mod Q. It is basically the diagram here, but in the algorithm kind of process. So it is useful for the learning part. So the other scheme is digital signature standard, which is the most commonly used technique as of now. So the DSS was adopted by NIST in 1994 based on the Elgamal scheme with the idea from Schnorr scheme. So it is basically again based on the Ellis scheme, which was the first and the primary scheme. So it is just modified a bit. So Ellis chooses a prime P. Again, it chooses a random number. The number of bits in P must be a multiple of 64 and chooses Q 160 bits in such a way that Q divides P minus 1. So Ellis uses ZP, X and ZP. So Ellis creates E1 to be the Qth root of 1 modulo P by calculating E1 is equal to E0 into P minus 1 upon Q mod P. Ellis chooses D as a private key and calculates E2 is equal to E1 power D. Ellis public key is E1, E2, P, Q and her private key is D. So there's that. The DSS scheme is also given here in the diagram. So we can see the diagram, and now we have to see the DSS versus RSA. So RSA is another signature algorithm. So it is also a digital signature algorithm. The computation of DSS signatures is faster than the computation of RSA signatures when using the same P, and the Elgamal, the DSS signatures are smaller than the Elgamal because it uses less byte to store the same amount of data, and it just has to be a multiple of 64 because Q is smaller than P, as obviously. So the variation. So the timestamp, sometimes a signed document needs to be time stamped to prevent it from being replayed by an adversary. This is called timestamp digital signature scheme. And the blind signatures, that David Chum has developed some patented blind digital signature scheme. The main idea is as follows: the Bob creates a message and blinds it. Bob sends to the blind message to the Elise, and Elise sends the blind message and returns the signature on the blinded message. Bob unblinds the signature to obtain a structure on the original message. So this is the blind signature scheme and the time stamp signature scheme. So what are the applications of digital signature? The applications of digital signature are, most of the applications directly or indirectly require the use of public keys. To use a public key, a person should prove that she actually owns the public key. For this reason, the idea certifies that the certificate authority has been developed. So these are the protocols which are used in the digital signature scheme. So that's all for the video. Thank you so much. Hope you liked it.